Hello everyone, my name is Priya Goyal and I am excited to present our paper titled Fairness Indicators for Systematic Assessment of Visual Feature Extractors. Our motivation behind this work is twofold. Number one, vision models are getting big and deliver excellent low-shot performance. This means the models can be used off the shelf for any downstream applications. This necessitates that we understand the harms and biases of models, especially in an out-of-domain context, since the exact application of the model is difficult to predict. Number two, facilitate the progress towards building models that work for everyone and everywhere. We provide fairness indicators that can allow measuring, comparing, and tracking the progress of new developments in computer vision, and these indicators can be used on all computer vision systems. We hope that these indicators will make it easy to diagnose harms and biases, and thus help facilitate or even mandate the fairness assessments in computer vision research. We briefly overview related work in this presentation and refer viewers to our paper for more details. There have been a lot of efforts and work towards measuring harms and biases of models in computer vision. Some works that are noteworthy include: number one, OpenAI CLIP paper that shows the fairness evaluations. However, the evaluations and the procedure used is specific to the CLIP type model that uses text for prompt engineering instead of visual features. Further, there was no systematic setup proposed that can be used to audit the fairness of all other types of computer vision models. Other line of work involves explicitly measuring harms and biases for different attributes like gender, age, skin tone, etc. However, these works involve training an attribute-specific classifier, and a lot of ethical concerns have been raised around this. And last, another important work involves measuring geographical diversity and testing if the model can recognize objects equally across the world. However, this line of work does not account for spurious correlations present in the dataset, such as large number of images from the same household. We propose 3 indicators that are applicable to any visual system. These indicators leverage publicly available datasets for fairness measurements, such as casual conversations, OpenImages MIAP, etc. Our indicators are of 2 types broadly speaking. Type 1 measure the harms or biases of a fine-tuned visual system, and Type 2 measure the harms or biases in the raw embeddings of a visual system. We discuss these indicators in detail next. Our first indicator, based on similarity search, allows measuring harms such as misgendering. It's based on similarity search and no classifier is involved. The exact setup is as follows. For datasets, we use UTK faces as database and casual conversations as queries. The task is similarity search, and our goal is to measure disparities between sensitive groups in learned representations of images of people. The sensitive groups can be anything, including gender, skin tone, age, etc. And the metric is precision at k, where k is 5, 10, etc. Our second indicator allows measuring harms, such as stereotypes, denigration, etc., based on the labels that models assign to a photo. The exact setup is as follows. For datasets, we use casual conversations, which contains photos of people's faces, and OpenImages MIAP, which contains people in more realistic day-to-day settings. And the task involved is image classification. Our goal here is to measure associations between harmful predictions for images of different sensitive groups. The sensitive groups can be anything, including gender, skin tone, age, etc. And the metric is percentage of harmful predictions at various confidence threshold. We recommend using the confidence threshold so that we can appropriately handle the cases where the model makes harmful predictions with a very low confidence score versus a harmful prediction with a high score. Our third indicator allows measuring if the models can recognize objects across the world and across different income level spectrums. The exact setup is as follows. For datasets, we use $Street dataset that contains images of objects across 4 different regions of the world: Asia, Africa, Europe, and the Americas. Further, images have income level metadata available, and the income is bucketed into 3 groups: low, medium, and high. The task involved here is image classification, and our goal is to measure disparity in object recognition depending on the household income and different regions of the world. The sensitive groups are the income households and the regions of the world. The metric is the object recognition hit rate, where we first deduplicate the data. Same image can appear many times in the dataset, but with different labels. So if the model predicts any of the labels for the image, we count it as a hit. We further compute the average hit rate per household, that is, over the images belonging to the same household. We validate our indicator's effectiveness on 16 models that vary in training paradigm, such as supervised learning, weak supervised learning, or self-supervised learning, and their model or data scale and data domain. In weak supervised learning and supervised learning, we use labels and train classifiers to predict those labels. However, in self-supervised learning, we have no labels available, and the models are trained to learn some pretext task defined by the self-supervised learning. The results of our first indicator demonstrates that female with darker skin tone has lowest precision amongst other sensitive groups. There is also large discrepancies between male and female for ImageNet models. And increasing the data size in general helps with reducing discrepancies. Self-supervised learning overall reduces discrepancies drastically, but except for female with darker skin tone. And lastly, model scale reduces discrepancies further for self-supervised learning, but not for supervised learning. The results of our second indicator demonstrates that self-supervised models consistently requires small confidence threshold to push harmful prediction rates close to 0. However, supervised and weak supervised models start off with notably higher harmful prediction hit rates and take longer to lower their prediction rates close to 0. Self-supervised learning paradigm results in the lowest harmful and the highest non-harmful hit rates. Further, supervised signals, including supervised and weak supervised results, in more harmful associations and larger harmful association hit rate differences across different groups. Self-supervised learning on ImageNet leads to overall slightly lower harmful predictions than self-supervised learning on Instagram. And we think this is possibly because ImageNet data domain is more object-centric. However, this trend is reversed for non-harmful predictions. For self-supervised learning on Instagram, data scale helps, meaning non-harmful predictions increase and the rate of harmful predictions decreases. The results of our third indicator demonstrate that weak supervised learning and self-supervised learning improve over supervised training, and self-supervised learning on Instagram is significantly better. Data scale improves generalization, and improvement is most for non-Western and low to medium income level households. And lastly, model scale helps, especially training on larger data sets. Besides confirming some existing discoveries of harms and biases of models, we overall find that self-supervised models trained on large amount of uncurated internet data are more promising. We also note the limitations of these indicators. The indicators are ever evolving to capture new model types and new types of harms and biases. The indicators are currently using the datasets that are publicly available for measuring fairness. However, these datasets themselves have limitations in data size and the availability of the labels for all the social and demographic attributes. Please read our paper to learn more or visit our virtual booth. Thank you.